All right, today we're diving into a really landmark idea in AI, the Neural Turing Machine. It's this concept that tried to solve a huge problem by giving an AI something we all take for granted, a simple notepad. So let's get into how this pretty simple idea totally changed the game for AI memory. So think about it like this. For the longest time, neural networks were awesome at pattern recognition, right? Like spotting a cat in a photo, no problem. But what if you asked it to remember a string of numbers and then, say, repeat it back? Well, that was a whole different story. They just didn't have a reliable memory, no real way to store and pull up information to solve problems that take more than one step. And that's exactly the challenge the Neural Turing Machine was designed to take on. The solution that was proposed way back in 2014 was honestly pretty revolutionary. Instead of just trying to build a bigger, better neural network, the researchers decided to create a hybrid. They were going to merge two completely different worlds of computation to get the best of both. And this slide just breaks it down perfectly. On one hand, you've got neural networks. They're brilliant at learning from messy, real-world data. That's their superpower, this fuzzy pattern matching. But they're not so great with structured memory or precise step-by-step logic. Then, on the other hand, you have your classic computer. It's got perfect memory, and it's incredible at running algorithms. But it can't learn from examples the way a neural net can. The big goal here was to build a bridge between these two worlds. And this is what they dreamed up, the Neural Turing Machine, or NTM for short. It was engineered from the ground up to get the best of both worlds, to take that intuitive pattern-matching skill of a neural network and fuse it with the precise algorithmic muscle of a computer. What you get is an AI that can both learn and compute. Okay, so how in the world does a machine like this actually work? The whole setup is actually surprisingly intuitive if you use a simple analogy, a brain with a notepad. Let's break down what those two parts are. So first, you have the brain. This part is called the controller, and it's a neural network. A lot of the time, it was a specific kind called an LSTM, which stands for Long Short-Term Memory Network. This acts as the central processor. It takes in information, it processes it, and it learns what to do next. This is the part that's doing all the thinking. But here's the real game changer. That controller, the brain, is hooked up to an external memory, our notepad. This is a dedicated memory bank where the AI can choose to write things down that it wants to save for later and then decide when it wants to read them back. It's actively managing its own memory. That's huge. And this pretty simple idea led to some really powerful results. Just by being trained on examples, and this is key, with no one explicitly programming it how to do the task. An NTM learned to perform simple algorithms. It could copy long sequences of information, it could learn to sort data, and it could even do something called associative recall, like learning that a key goes with a certain lock. These were all things that traditional neural networks really struggled with. So the 2014 paper was a massive breakthrough. But an idea is one thing. Making it actually work, that's something else entirely. The journey from the theory on paper to a stable working model was, well, it was a long and rocky road for the whole AI community. Here's what happened. After the paper got published by Alex Graves and his team, the original authors didn't release their code. And that kicked off this 4-year-long quest where researchers all over the globe tried to replicate their results. But it turned out to be notoriously difficult. It actually wasn't until 2018 that the first really stable open source version was published. And it was such a big deal that it won a Best Paper award. So why was it so hard? Well, developers kept slamming into these major hurdles. One of the most common issues was that the gradients, those are the signals the network uses to learn, would become something called not a number, or NaN. You can think of it like the AI's internal compass just shattering. The whole learning process would just spin out of control and the training would fail completely. And even when you could get it to work, it learned at a snail's pace. It was just really unstable. But despite all those challenges, the idea behind the Neural Turing Machine was just too powerful to ignore. So while you probably won't find many NTMs in production today, its legacy, conceptually, it's immense. At the end of the day, the NTM was a vital proof of concept. It was that it can be done moment. It showed the world that it was actually possible to create a system that could learn how to use an external memory. And that foundational work directly inspired the next wave of more advanced, more stable models like the Differentiable Neural Computer, which took the NTM's core ideas and made them even better. And this is really just how science works, right? One paper, one core idea gets documented, it gets shared, and it can spark years and years of research and new innovation across an entire field. It's pretty cool. And it all comes back to this one powerful central idea, this quest to combine the fuzzy pattern matching capabilities of neural networks with the algorithmic power of programmable computers. I mean, that one sentence, that really captures the ambition and the importance of the neural Turing machine perfectly. So this leaves us with a really fascinating question to think about for the future. The NTM was an early step, for sure. But this fundamental idea of giving a learning system a structured memory is more relevant today than ever. It makes you wonder, what kind of intelligence are we going to unlock as we get better and better at bridging that gap? That's a question that researchers are still racing to answer.